So one important application of the normal distribution is that I can use it to approximate the binomial distribution, and I can do it under certain conditions, but I will get onto those. Let's first take a look at the binomial distribution, and this is a binomial distribution. So this is it done out mathematically, with n in this case equal to 40, I think it is. Oops. Well, it was n equal to about 30 or 40 and p equal to 0.06. And you can see that this is a dynamic worksheet, so I can move it around. So if I set p equals to 0 or very low, you see it all goes to the far left, and if I set p equals to 1 or very high, it all goes to the far right. So it behaves quite how we're used to doing it. And you notice something, and I'm just going to make n a little bit larger, maybe make n close to 150. And of course I'm going to need to change my axes to be able to see that. So let's make x max 160. Where's my apply button? I think that's done it. And what do you notice about this? What does this look like? This begins to look a lot like a bell curve, right? As in, it's got that whole shape where it's very, very bell-like. And again, this actually gets better and better the bigger I go. So again, if I went up to maybe 610, there we go. So again, let's have to play around with our axes a little bit. And this is where it gets a little bit tricky. So graphics. And I'm going to set this is equal to 0.2 now, I think, and we'll go up to 500. Now what does it look like? It looks almost like a perfect normal distribution, right? That's basically the bell curve that we're used to seeing. So it turns out that under very, very certain circumstances, a binomial distribution and a normal distribution, they're basically the same thing. So we can use our normal distribution to approximate the binomial distribution. So I promised you there were certain conditions that needed to be met. So let's just try and formalize some of this. Let x be a random variable that is binomially distributed with n trials and probability of success p. Then, under these two conditions, firstly, if n is large, and by large this is very poorly defined, but 50 is a roundabout number, so let's say n bigger than 50, and if the probability of success is quite close, is not too small, so it's not too extreme, not too skewed, so we say in this case np must be bigger than 5, and nq, which is equal to n1 minus p, must be less than, must also be bigger than 5, sorry. If these two conditions are met, I can approximate the x by a normal distribution. But if I think about it, what's the mean of this normal distribution going to be? Well, it's just going to be the mean of this one, which is np. And what's the variance of the normal distribution going to be? Well, it's just going to be npq, right? Where q is 1 minus p, if you recall. So, why is that? That's because npq is, of course, the variance of the binomial distribution. So under these circumstances, we can say that this discrete distribution has a continuous approximation. And this was very, very useful more back in the day, where binomial is very tedious to calculate because it's discrete, whereas we know normal very, very precisely. And we've studied the normal distribution a lot. So it makes it very easy to calculate approximate binomial probabilities. But also if you're doing binomial trials with a very, very large value of n, into the millions or billions or trillions, then that can also slow down and take up a lot of computer power. So often an approximation using the normal distribution is faster when we're dealing with a lot of data or dealing with a lot of trials. But there's something we just need to be a little bit careful of. So if I go and look at this, what happens when I zoom in here? I mean, this looks normal, but when I zoom in, I see that it is still actually rough, right? It is still lumpy. And in particular, you look at where the bars are. So the bar, the histogram, lies not on top of 355 here, but it lies just, it lies 0.5 to the left and 0.5 to the right, and it covers a width of 1, right? So this is the idea. is that if I want to know something like the probability of 355, what is the probability that x equals to 355 under the binomial, where x is still binomial? Well, we know we can actually calculate this. This has a number, it has a value, right? It's what was that n and all that? It's 610 choose 355. Then our probability p is where is it? 0.63, so 0.63 to the power of 355 times 0.37 to the power of 610 minus 355, right? And this is a horrible number, but it's just a number. There is a value. But if I take a look at a normal distribution, right? Something with a normal distribution, what's the probability that this one equals to 355? Well, that's 0, right? We've already talked about this, where a continuous distribution can't take on a particular value. So instead, how do we do it? We don't look at how does it equal that value. We look at, does it lie within 0.5 of that value on either side? Or rather, you can think of it, would I round to that value, right? So here I'd instead consider the probability that 3.5, sorry, let me start on a new one. Here I'd then consider, so we already worked out probability x equals to 355 ought to be 0, so we can't have that. Instead, I'd do the probability of 354.5 less than or equal to x less than 355.5, right? And that's precisely what's over here, right? It's between 354.5 and 355.5. Now, I've included this less than and equal to and this less than because this makes everything neat, but as you well know, I can ignore the equals to sign if I need to, right? Because this is now a continuous distribution. So this is what we call a continuity correction. Because I'm going from a discrete distribution to a continuous one, I need to make this continuity correction to account for the extra space that I now have, to account for the fact that I can no longer have something exactly equal to it, so I need to take plus or minus 0.5 around about it. So let's take a look at an example. Where have I got it? Let's look at example, and okay, so here it is in your notes as well. So equals to k, so we have to look at plus or minus a half here as well. Yeah. So example 10, given that, and I'll just trust that you guys can go through these in your notes alongside me. So we're just going to work out a few of these probabilities, right? So example 10. So we're given that x is binomially distributed with n trials and probability p. And we know then that x can also be approximated by a normal distribution, np, npq. So we want to carry out the continuity corrections for the following. So the probability that x equals to 2, well, that means that I want to look at the probability that x is between 1.5 and 2.5. The probability that x is between 3 and 5, and so this is in a discrete situation. So in a continuous situation, what would I have? Well, if we think about this a little bit, it means that if this is my bars, 3, 4, 5, x between 3, 4, and 5, I might have something that looks like this, right? In which case, I'm now looking at the area from 2.5 until 5.5. So this means that I want 2.5 to be less than or equal to x less than or equal to 5.5. Yep. So again, we don't do anything funny. We just look at the last one and we add an extra half to account for the continuity correction. And look at the last one, add an extra half on. Yep. So part 3, what do we have? We've got the probability that 3 is less than x is less than or equal to 5. Again, this is in a discrete case. So in a discrete case, this means the probability, we're actually looking at 4 less than or equal to x less than or equal to 5. And so now applying a continuity correction, that means I'm looking at 3.5 less than or equal to x less than or equal to 5.5. 4, the probability that 3 is less than x is less than 5. Well, if this is a discrete case, that's just the same as saying the probability that x equals to 4. And again, we've already seen how to do that. That means we're between 3.5 and 4.5. So we're looking at the probability that x is less than or equal to 3. So this is just going to be the probability that x is less than or equal to 3.5 in the continuous case. And part 6, looking at the probability that x is bigger than 5, that's equal to the probability that x is greater than or equal to 6. And so again, you think about what this means for our graph. That means I've got 6 here, I've got 5 here, I've got 7 here. Like, let's say it looks something like this. And it's maybe going up some more after that, I don't know. Right? That means I want bigger than or equal to 6. It means I want everything in this area. So I'm starting from 5.5. So this means I'm looking with continuity correction, x bigger than or equal to 5.5. So again, I'll pause here and then we'll do examples 11 and 12 in a separate video. But any questions, please feel free to post them here and now.